All right. So we're going to look at tangents, lengths with parameterized equations. And we're going to notice a good, neat thing about the notation, specifically Leibniz notation, and that we can treat derivative and differential relationships as if they're fractions. And so if we have a parameterized curve where x is some function of t and y is some function of g, or some other function of t, I should say, called g, um, and is differentiable with respect to t. Then in the point on the curve is also differentiable function of x, y, and t. And so we get the differentials, right, that dx dt is equal to f prime, dy dt is equal to g prime. And all said and done, we can put these together. As long as the change with respect to x does not equal 0, then we can create a relationship here. And this is related by the chain rule. So if we have dy dt, well, so the function of y with respect to t is the same as dy dx times dx dt. Now, I always like that if you were to cancel out these parts of the fraction, you'd get dy dt. The chain rule does recreate fractionally how the differentials relate to each other. And since we are kind of collecting the respective change and the ratios of change, even though we've learned to take the limit down to an instantaneous point, this makes notational sense for it to work that way. So let's solve for dy dx, which is the slope that we would see at a given point in our regular notation. Dy dx represents slope on an xy plane. And so if we solve for dy dx, I'm going to divide the right-hand side by dx dt. And so we have the slope of a parametric curve, dy dx is given by dy dt divided by dx dt. We can extend this and we can say that we can take the second derivative, or the acceleration or the rate of change, and we can say that is the same as d dx of y prime. Okay, y prime is giving us a value of the parameter. And if we take the derivative of y prime, we find that we get dy prime with respect to t over dx dt. So keep note of y prime. And y prime is dy dx. So the derivative dy dx of the previous dy dx, we take the derivative again. And also given that dx dt, of course, does not equal 0. We're able to find the second derivative, or how a curve is changing parametrically. So I'm going to go into examples. Again, I'll use the example in the book. So we're going to have a parametric curve where x is equivalent to the secant of t and y is equal to the tangent of t. Now, both of these have asymptotic behavior and they have a natural period where from negative pi over 2 in an open interval, because they're asymptotic at pi over 2 and negative pi over 2. And so we're able to have an open interval that these parameterize for. Oddly enough, because they're undefined, as we get closer to pi over 2, y will go off to infinity. And as we get closer to negative pi over 2, or as we get closer to, let's see, 0, then this has asymptotic behavior. 0 for the t parameter. Let's make some values of t. I think I said that backwards. And so we're definitely going to check it by making some values of t. So, well, I can't be at negative pi over 2, but I can be at negative pi over 3. I can be at negative pi over 4. I can be at negative pi over 6. 0. Pi over 6. Pi over 4. And pi over 3. And so we'll look for the values of x and the values of y. And let's see, so secant of t is equal to 1 over cosine of t. And so at negative pi over 3, cosine is 1 half, so the inverse is 2. At pi over 4, negative pi over 4, all cosine values are positive, right? So all of these values are going to be positive. The tangents will be negative here and positive here. So negative pi over 4 is, the cosine is root 2 over 2, so this is 2 over root 2, or 2, let's see, so 2 over root 2, which is equivalent to root 2. And then a negative pi over 6 is when cosine is root 3 over 2. So this would be 2 over root 3, or 2 root 3 over 3. And at 0, cosine is 1. So this is 1. And then it walks back up these values, 2 root 3 over 3, root 2, and 2. So it looks like 1 is the smallest value, and then it increases, and x increases. And then for y values, this is sine over cosine. So the cosine value, I'll have to write some of these out. So negative pi over 3 of tangent. So our tangent starts at, let's see, this is going to be negative root 3 over 3. This will be negative 1, negative root 3. I have that backwards. That's negative root 3. That's negative 1. That's negative root 3 over 3. This is 0. Then we're going to go root 3 over 3. 1 root 3. Well, that wasn't too difficult to try to imagine, but let's graph it now. So the smallest x value is 1, and at 1, y is 0. So we'll make 1 out here. I will go upwards in x, so root 3 divided by 2 root 3 divided by 3. 1.6, 1.5, roughly. Let's see. Root 3 over 3.5. We're going to say somewhere around here and here. Root 2 is 1.4. So when y is 1, which is this distance here, so up here, then n we're at 1.4. Both sides. And then when we hit 2, we're at root 3, which is like 1.69-ish. So we're just ahead of 1. We get something that looks kind of hyperbolic. If I were to run over to Desmos and graph this, I'm not recognizing the curve directly, but it definitely has a kind of hyperbolic behavior to it. And we're going to look for the tangent line when t equals pi over 4. And so when t equals pi over 4, we're here at x values of root 2 and y values of 1. So what we want to be able to do is we want to find the tangent line. What we're going to use slope-intercept form, so we want to find the slope. So dy dx will be dy dt over dx dt. So we'll take the derivative of secant, so that's secant squared t, and we'll take the derivative of tangent, which is secant t tangent t. We'll get a cancellation here, so we'll get secant of t over tangent of t as our slope, and we'll want to evaluate the slope at t equals pi over 4. So the secant of pi over 4, let's see, the secant of pi over 4 is root 2, and the secant of pi over 4 over tangent of pi over 4. And pi over 4 is that beautiful place where the tangent equals 1. So this is root 2. So we have a slope of root 2. I guess I'll be overly dramatic here. We have a tangent line. I'll line it up. And we'll say this line m equals root 2. So y minus y1 equals root 2 times x minus x1. So y minus, and we go back to where t equals pi over 4, 1 equals root 2 of x minus root 2. And so y minus 1 equals root 2 minus 2, root 2 of x. And y equals root 2 of x minus 1. And we have our tangent line. So in parameterization, we're able to look at the space and use our differentiation rules to find slope within our common definition of slope, which is how the y is changing with respect to x. I'm going to look at taking second derivatives and looking at a asteroid, and on the next video I'll do examples of those, and then on the third video we'll look at lengths of curves and go back to our cycloid, which I said we'd be coming back to.